All right, so in this video, we're going to be taking a look at significant figures, and you might hear them called sig figs in short. And we're going to take our time going through this. So I want you to write down what you think the correct volume of water is in this graduated cylinder. We can make a pretty good estimate here, but it will be an estimate, and you'll see why. And so if we take a look at just the graduated cylinder itself over here, you can see that the 20 mil mark is right here, and then we've got the 21 mil and the 22 mil, 23 mil, 24 mil, and 25 mils, right? So you know that the volume of water is somewhere above 20 milliliters and somewhere above 21 milliliters, right? So you can see that easily in this picture. We've got 20, 21, and 22 milliliters, but we haven't quite reached the 22 milliliter mark. Remember, you read the volume of a liquid inside of a graduated cylinder at the meniscus, and that would be this bottom portion right here. It is not the highest point on the corner. All right, so we know that we're above 21 milliliters, but we're not at 22 milliliters, right? So you can make your estimate here, right? 20, 21, but we're not at 22 yet. So, here's the thing. Looking at it, to me, it looks like it might be, maybe 21.6 or 21.7. But if you told me you thought it was 21.5 or even 21.4, or if you said it was 21.8, I couldn't count it wrong because we don't know. We can only make as good of an estimate as far as volume goes as the quality of our glassware that we're using, right? Now, if the glassware had more tick marks, that is, it was a more accurate piece of glassware, then we wouldn't just have 20 mils and 21 mils and 22 mils. We'd have individual smaller marks in between, right? But we don't have that. So the best we can do is 3 significant figures, right? 21 point whatever the estimated digit is. But notice that all of these numbers here to the right of the decimal are estimated. All of the numbers to the right of the decimal are estimated. And so we're going to take this idea and we're going to run with it in this concept. So what are significant figures? Well, again, we know that it's at least 21 mils. And we're certain that the measurement is at least 21 point something, making it 3 significant figures, right? And we can somewhat accurately measure it, right? So here's the deal. Significant figures in a measurement always include the following. All of the digits known precisely, and in this video that was 21, plus one last estimated digit. But notice, even though it's an estimated digit, right, and we can only estimate it based off of the quality of the glassware or the instrumentation that we're using, that is still considered a significant figure. So 21 point, really whatever you guessed in the earlier slide, right? And so we're going to take a look again at that right here, not using glassware, but using a ruler. And so I ask you this question, but before we answer question number 1, let's take a look at A, B, and C, right? And so we have, if you can tell, 3 different qualities of rulers, right? A here has only got 1 mark, only 1 meter, right? And so, what if I ask you to measure a quarter of a meter, right? I mean, you would have to totally estimate. And as you see here, you've only got 1 significant figure. And again, remember I told you in the other slide, sig figs always include 1 estimated digit. Well, you've only got 1 significant figure here. So that means, that this 1 significant figure is estimated. And it's obviously estimated, right? This is measuring 6/10 of a meter. You could cut this in half and you could say, well, 6/10 might be somewhere here, but that's totally estimated, right? So that's very low accuracy. You would call that a piece of junk. And ruler B, or I guess I should say meter stick B, it's a little bit more accurate. Instead of just going all the way up to 1 meter, you've got it's divided by 10. So you got, 0.1, 0.2, so on and so forth. And, we're looking at 0.6 again. But this time, we know for 100% that it is at least 0.6. We know this is for sure, but remember, significant figures always include one estimated digit. So we know the 6 for sure, but this time the 1 is what's estimated, right? So because we have more accuracy, that is more tick marks in our meter stick this time, we can measure one more significant figure. So ruler B is a little bit better quality. Taking a look at ruler C, again, we're 100% sure that the wooden block that we're measuring is at least 0.6. And we're also for sure, right, because we have more tick marks in between the 6 and the 7, that the 0 is 100%. But the last digit, again, always, is the estimated digit. So in this case, the 7 here is the estimated digit. But because we have more tick marks, more accuracy in our measuring device, we have more significant figures. So that means ruler A is the least accurate and C is the most accurate. But here's the problem. Which one do you think costs more? If you said ruler C costs more, there's no doubt about it, right? This has the most cost. And that's an issue. So the question is, in science, and really when you're dealing with anything like this where you have to purchase equipment, you have to think about the best value for the dollars that you have to spend. If ruler A cost $1, which would be way too much, right? You would be stupid to waste $1 on it because you couldn't do anything with it. So it's junk. Ruler C, and again, this is just totally made up. If this were $5, okay, but what if you needed to buy 100 of them for your class? And it's very, very accurate, but for some lower level classes, ruler B might be sufficient. So that only costs $2.50, right? So that means the difference between these two is 1/2 price. And, if ruler B could get the job done, that's might be what you select. And so, there's definitely a correlation between accuracy and significant figures and cost. But you might wonder, again, how did I know, particularly, you might have been asking yourself the question, how did I know that there was 1 sig fig here, 2 sig figs here, and 3 sig figs here, right? And so we're going to go ahead and figure that out. So estimate the volume of this graduated cylinder and give the correct amount of sig figs. So before I tell you the rules for sig figs again, let's just go ahead and do this practice. So remember the definition of sig figs from the other slide. All known digits plus 1 estimated digit. All right, so looking at this graduated cylinder, we know that we've got 50. This is 51, 52, 53, and 54. We don't have 54, but we do have at least 53 milliliters. But we have to have the estimated digit. So we know we're going to be 53 point something, right? So again, 50, 51, 52, 53. If you want to say 53.5, that's fine, but it could be really 53 point anything because it is the estimated digit. So that means you would have 3 significant figures here. Now, if I gave you 100 different numbers and I said, tell me how many sig figs are in each of these 100 numbers, you would have to understand the rules for sig figs. And to be honest with you, a lot of teachers and pretty much every textbook will go through a list of like 4 or 5 rules. And for some of you with analytical minds, those rules make a lot of sense. But for me, it's just jumbled up, whatever. So I teach the Atlantic Pacific rule for significant figures. And with this rule, you honestly just have to know the location of the Pacific Ocean, which is over on the west side, and the Atlantic Ocean, which is over on the east side. And if you know that, you can pretty much forget all the other stupid long rules. And so here's a map of the United States. The Pacific Ocean's over on the west coast by California and all those states, and the Atlantic Ocean is over on the east coast around the Carolinas and D.C. and all that. And if you know that, you're going to be in pretty good shape. But let me tell you why we're concerned about the Pacific Ocean and the Atlantic Ocean. All right, so here's the deal. If you have a number and the decimal is present, like 1.25, you're going to start counting significant figures on the Pacific or present side. That means you would start counting your significant figures this way, because this is where the Pacific Ocean is located. Now, if your decimal is absent, right, you're going to start, well, and again, an example might be 1,000, right? You're going to start counting significant figures on the Atlantic side, which is going to be coming on in from this way, right? And that's it, right? Now, here's what you have to understand, though. Whether it be the Pacific side or the Atlantic side, no matter what side you start counting from, if it is a 0, it is not significant. You only start counting significant digits when you hit your first non-zero digit. So only start counting when you hit the first non-zero number. And then every number after you hit that first non-zero digit, even if it is a 0, is significant. So after that, all numbers, even 0, is significant. All right, so let's take a look. And I know the writing is not the best, but it is what it is. So let's take a look at the 1.25. The decimal is present. So we start counting significant figures on the Pacific side. And when you hit your first non-zero digit, that number and every number after it, regardless of what it is, until you reach the end of the number, is significant. So we're starting over here on the Pacific side. The first number we hit is non-zero. That means this number and every number after that, regardless of what it is, until we hit the end of the number, is significant. So therefore, we have 3 significant figures. Let's take a look on the Atlantic side. The 1,000. So the decimal is absent. We start counting at the side where the Atlantic Ocean would be. We look for our first non-zero digit, and that's actually not until we hit the 1, right? So these 3 zeros aren't significant. Again, we're moving in this direction, the side of the Atlantic Ocean. When we hit our first non-zero number, that number and every number after it is significant. But the problem is we've only got the 1. So that means we have 1 significant figure here. And that's the Atlantic Pacific rule. So let's do some more examples here. This first example, we got point. Well, you know what? Again, is the decimal present or absent in this first one? Right? It's present. So we're going to start counting sig figs from the side where the Pacific Ocean is. And we start counting sig figs, again, moving in this direction, once we hit our first non-zero digit. And after that, every number is significant. So moving in this direction, this 0 is not significant, neither is the second one, neither is the third one. But we hit our first non-zero number, and we move on, finishing the direction of the Pacific Ocean, right, until we hit the end of the number, and every number is significant. So that means we have 2 significant figures in this number. So let's take a look at the next one. Again, the decimal is present, so we start counting on the Pacific side. We look at our first number, it happens to be non-zero. That means this number and every number after it moving in the same direction is significant. So that means all of these numbers are significant figures. Looking at 2,500, the decimal is absent. So we move in this direction now. and we look for our first non-zero digit. That would be the 5, and we're going to continue moving in the same direction that we started. That means that number, the 5, and every number after that moving in that way is significant. So that means the 2 and the 5 are, and we have 2 significant figures. Now, when you have a number in scientific notation, right, this is base 10, so it's just dealing with zeros. You can pretty much ignore the times 10 to the whatever power. Who cares, honestly? So the decimal is present. We start on the Pacific side. The first number that we reach moving in this direction is non-zero. So this number and every number after it continue in that direction is significant, meaning you have 3 significant figures. Right? This number, again, the decimal is present. You start on this side. The first number is non-zero. So that number and every number after that, even if it's 0, is significant. Okay? Man, I seem to favor the present in this one. So again, the decimal is present. You start moving in this direction, and the first non-zero. Oh man, the first non-zero digit number that we hit. Sorry about that. Is the 1. That's the last number. So we got 1 significant figure. This last example, the decimal's present. First number you hit, my friends, when you're moving in this direction is a non-zero number. So that means everything here is significant. But you know what? Let's do. So that we have the number 100,000. This is a good example, actually. So the decimal is absent. We start on the Atlantic side. You can see that the decimal is going to make all of the difference. You start on the Atlantic side because the decimal is absent. Moving in this direction, you don't start counting sig figs until you hit your first non-zero digit number, which is the 1, and it's the last digit. So you have 1 significant figure here. But what if I trolled you and did this? Just randomly put the decimal right here, which is pretty interesting, right? Because now the decimal's present, so you have to start counting from the Pacific Ocean side. And it just so happens the first number you hit is non-zero. So by definition, that number and every number after that is significant. So that would make all 6 a significant figure. So anyway, sorry about that. That was already there, but whatever. All right, so now let's, if I were you, I would pause the video and see if I could work these. And I'm going to put the answers up in just a minute. All right. So again, this is absent. So you have 1 sig fig, right? This is present. So you have 3 sig figs. This is present, so they're all significant. I was just too lazy to count. This is present, so you have 3. This is present, so you have 4. And this is absent, again, so you're moving in this direction. These zeros don't make it, but these do. Okay? And so let me also point this. We'll go ahead and cover this while we're doing this video, right? The more accurate the equipment you're using, the more significant figures you measure. We've already talked about that, right? So when you're dealing with glassware, right? For example, you never use a beaker to measure volume of liquid, right? You would use something more accurate like a graduated cylinder, I guess, or more preferably a volumetric flask, right? Or even a burette if you want to mess with that. So, the more accurate piece of glassware you use, the better data you're going to get, right? And again, the most accurate piece of glassware is traditionally your volumetric flask. The burette really also, but we don't tend to use those very much unless we do like a titration of some type. The beaker is least accurate, and if you think about it, right, a volumetric flask has a pretty narrow neck, and then the bulb gets bigger at the bottom, right? That's not a good picture of a volumetric flask at all. But if you go back a couple slides, you'll see what I'm talking about there, okay? The beaker, it does not have a narrow neck, right? It's just more like this, right? And so the narrow neck matters, right? And you can verify this, which we will do in class. 1 ml of water is 1 gram of water. So in an experiment that you can do and that we will do, I'll give you 4 pieces of glassware or so. I'll give you a beaker, I'll give you a graduated cylinder, I'll give you a volumetric flask, and an Erlenmeyer flask. And I might tell you to put 20 grams, or I might tell you, fill each up to the 20 mil mark, and then I'll have you weigh it on a scale, and you'll find that the most accurate piece of glassware, the volumetric flask, will be the one that weighs closest to 20 grams. The rest will be off quite a bit, right, just due to accuracy. So accuracy and precision is a big thing, right, to be accurate and precise. Here's a good example of that. You've seen these, though, forever. These are precise because they are all in the same range, but they're not accurate because it doesn't hit the bullseye. And these aren't precise because they're scattered, and they're sure not accurate because they're nowhere near the bullseye. All right? Have a good day.